Welcome to the beginning of another unit in the calculus program. Before we get into it, let's go ahead and get started with these warm-ups as a reminder of what we've already learned and to get us ready for what we're about to see. So in number one, it says f is a differentiable function such that f of 3 is 15, f of 6 is 3, f prime of 3 is negative 8, and f prime of 6 is negative 2. So it gives us those bits of information. And then it goes on to tell us that g is differentiable and that g is equal to the inverse of f. So we've got g of x is equal to the inverse of f of x. And we are looking for the value of g prime of 3. So I'm going to write that down here. We're looking for g prime of 3. Put a question mark there. So we need to be able to take the derivative of g. Now there is a short way of doing this, but it doesn't explain why it is what it is. So I would prefer to try and get rid of the inverse function in order to just deal with regular functions. So to do that, to get rid of the inverse function, what I need to do is take the f of both sides. So I'm going to go ahead and take f of the left and f of the right. By doing that, I end up with f of g of x is equal to x. And then from here, we'll differentiate. So on this side, we have to use a chain rule. So it'd be f prime of g of x times g prime of x. And then the derivative on the right is just 1. And since we're looking for g prime, I'm going to isolate g prime. So g prime of x is equal to 1 divided by f prime of g of x. So we've seen this plenty of times before. So from here, we're going to go ahead and plug in our value of 3 for x. So we've got g prime of 3 is equal to 1 over f prime of g of 3, because we're replacing x with the 3. So anywhere there's an x, I need to put a 3. So from here, we have to kind of look at what's given in order for us to evaluate this. Well, the first thing we need is to know what g of 3 is. And according to everything that was given, we don't know what g of 3 is directly. We only know values of f. But that's where this original function comes into play. It's so important that g is the inverse of f. So what I want to do is take note of this fact that for the function g, there is a coordinate that is 3 comma something. And we are trying to figure out the y value of this coordinate. Well, because f is the inverse of g, remember back to Algebra 2, or Math 3, depending on where you're at, the inverse functions take the x and the y's and they flop them. So if I'm looking for the y value of g, that implies I'm looking for the x value of f. And since the x value of g is 3, that means the y value of f is 3. So if I can figure out the f function, if I can figure out the function for which x value produces 3, then I'll know the y value that x produces on g, or that 3 produces on g. So I look to my given information and I notice that f of 6 is equal to 3. So I can put a 6 in here. So 6 comma 3 for f implies that g has a coordinate of 3 comma 6 because those switch. So now I know as a result of that g of 3 is 6. So I can just plug that in here. So I've got f prime of 3 is equal to 1 over f prime of g of 3 is 6. And now I need to figure out what f prime of 6 is. Well, it gave us that f prime of 6 is negative 2. So we can just substitute that in now. G prime of 3 is 1 over negative 2. And that is our answer for number 1. For number 2, this is going way back to Unit 1 and actually diving into a little bit of pre-calculus analysis stuff. It gives us an equation, it gives us a function where it says that y equals 5 plus 2 to the x over 1 minus 2 to the x. And it's asking us to find the horizontal asymptotes. So before we do that, what we need to recall is what is the definition of a horizontal asymptote. And you remember that a horizontal asymptote is a y value that a function approaches as x gets really, really big. It doesn't mean that it won't ever cross it. We could have, that's an asymptote of whatever this y value is. And this could also view a horizontal asymptote as the function trends toward a specific line there. So we need to remember the definition. A horizontal asymptote, by definition, is the limit as x approaches plus or minus infinity of the function of, we say maybe f of x, if f of x was the defined function here. So really all we have to do is figure out the limit as x approaches infinity and negative infinity. So let's go ahead and evaluate that. The limit as x approaches, first we'll deal with the positive infinity, of 5 plus 2 to the x over 1 minus 2 to the x. Well, if I go ahead and plug in infinity, I'll end up with 5 plus 2 to the infinity over 1 minus 2 to the infinity. And then as a result, we end up with 5 plus infinity over 1 minus infinity, which is infinity over negative infinity, which remember we call indeterminate. That is indeterminate. So we have to do some algebraic manipulation in order to get a numeric value out of this for the limit. So remember, when we're taking the limit as x approaches infinity, one very effective method is to divide by the highest power. In this case, our highest power is 2 to the x. So I'm going to go ahead and divide the top and the bottom both by 2 to the x. And as a result, I end up with 5 over 2 to the x plus 2 to the x over 2 to the x is just 1. And then over 1 over 2 to the x, and then 2 to the x over 2 to the x is 1. So I have this equation now. Now if I go ahead and plug in infinity, I end up with 5 over 2 to the infinity plus 1 over 1 over 2 to the infinity plus 1. And then from there, I end up with 5 over infinity plus 1 over 1 over infinity plus 1. And then we got to go back a little bit. Remember, when we're dividing by an infinite number, or a number that's really, really big, this fraction gets smaller and smaller and smaller, or it approaches 0. So 5 divided by a really large number is actually 0. And then the same thing on the bottom, 1 divided by a really large number is 0. So we end up with, oops, I carried over a plus sign. It should have been a negative here. So 1 over 2 to the x minus 1, minus 1, minus 1, and then minus 1. And then we can simplify this to say negative 1. And so there's one answer for us, and we'll put it in the proper notation in a minute. But then we have to look at the other side of things, the limit as x approaches negative infinity. Well, if I go ahead and plug in negative infinity into this form where I divided by the highest power, I'm going to get 2 to the negative infinity, which is going to move that up to 2 to the positive infinity on top, which is going to end up giving me an indeterminate form. Remember, when you're using different numbers, you got to try substitution first from the original function. So I'm going to just go ahead and plug in negative infinity into my original function here. So I get 5 plus 2 to the negative infinity and 1 minus 2 to the negative infinity. And then I can rewrite the negative exponent. I can put that down on the bottom there. So I get 1 over 2 to the positive infinity over 1 minus 1 over 2 to the positive infinity. And then as a result of that, I'll shortcut this a little bit. 2 to the infinity is infinity. 1 over infinity is 0. And then we have 1 minus 1 over 2 to the infinity. 2 to the infinity is infinity. And then 1 over infinity is 0 again. So we can simplify this and say 5 in simplified form. So we actually have two horizontal asymptotes here. And we can say, remember, a horizontal asymptote is a horizontal line with a y equals. So we'd say we have y equals negative 1 and 5 as our two horizontal asymptotes. So that wraps up the warm-ups for this lesson. Stick around for the lesson, the beginning of Unit 6, which is actually some pretty cool stuff.